Stock system naming for ionic compounds. Okay, so what I've done so far is I showed you a bunch of videos that has to do with basically come up with kind of the straightforward way of finding ionic compounds, names and formulas for ionic compounds using binary and tertiary ionic compounds. And that's what I teach in 110. But we need to go a little bit more in depth into it because you guys are in 121, and there's more complications involved. And so, for instance, is that I told you that copper has a charge of 2 plus. Well, how do we know that? Okay, and could it be something else, or more than one? And so that's kind of the thing we want to look at. We want to look at naming and come up with formulas for ionic compounds. And this is called a stock system. In basic chemistry, we go over charges for metals and nonmetals. There's certain patterns. Column 1 metals, the alkalines have a common charge of 1 plus 1 plus. Column 2 will have 2 plus. And it's kind of similar for the nonmetals, like fluorine is -1 minus. Everything in that column, fluorine's column, gets 1 minus. All right, everything in oxygen's column gets O2 minus. Everything in nitrogen gets 3 minus before it hits the zigzag line. And we'll see why that is when we get into the structure of atoms. Then there are some metals that don't have patterns. For instance, column 3 do not have a common charge at all. Okay, from column 3 to column 12, there doesn't seem to be any pattern. The pattern starts up over when you get to column 13, especially in the top part of the periodic table. Those elements will start getting common charges. First, the elements that seem to have predictive common charges are found in the first 2 and last 6 columns. These are called the representative elements. And this has to do with their electronic structure and how it relates to the periodic table. Most of the elements that don't have common charges per column, okay, are found in the midsection, are called the transition metals. That's 3 for 12. And also the inner transition down found at the bottom of the periodic table. What we're going to see when we look at the electronic structure of atoms, these elements here predictively look like they should have charges of 2 plus, just like column 2. But practically they don't have that. They do sometimes, but most cases you can't make that kind of assumption. All right, so what we want to really pay attention to is the elements that are found in the transitions, because they will have they don't have a specific common charge per column. Okay, and you have to be given them, and we'll talk how that relates here. In my 110 class and the beginning of this course, I told you guys this. You had to know these guys right here. All right, copper 2 plus, zinc 2 plus, lead 2 plus, silver, iron, and aluminum. These are the charges they have. Okay, and these are transition, representative. But this is kind of a weird representative. Okay, because it's in the same column as I believe carbon, but it's not a nonmetal, all right, because it's on the other side of the zigzag line, so it doesn't have the same charge as the element has a top of the chart. Then you have your transitions and then representative. Okay, so and we'll take a look at that. Aluminum is a representative element, and if you look at it, it's the third column over from the left in column 3. So in row 3, that should be. All right. Okay, so you go So it goes sodium, magnesium. Okay, and then there's this big empty space, and then you got aluminum. Okay. Well, this has a +1 charge, 1 plus charge, I mean. This has a 2 plus charge, and then this would have a 3 plus charge. So this is not, this shouldn't surprise you that this has a 3 plus charge. Lead, like I said, is in the representative elements, but it's odd because it's a metal. Okay, and it doesn't have the same charge as the nonmetals at the top. It would have a positive charge because it's a metal. Okay, many charges. Turns out that some elements, especially the transition elements, will have multiple charges. For instance, copper can be Cu2 plus or Cu plus. However, a few of them don't have multiple charges, like silver and zinc. So whenever you see silver, it's always going to be +1 plus, and zinc is going to be 2 plus. But this one, so copper and others, we're going to see in a minute. So if you just say copper sulfate, you don't know if you're talking about copper 2 plus or copper plus. So how do you know what elements have the multiple charges and which don't? All right. Well, there are a few ways to know this. These ways look at a periodic table that lists these. Now, not all periodic tables will have this, but I'm going to show you one that does. Okay. All right. So here's the periodic table. And I'm not sure which one you're going to use. By the way, you're allowed to use a periodic table for any tests. And I mean, this would be perfectly fine for a periodic table to use. Okay, so the one thing that you're going to notice is that it has numbers in the top right. Okay, and these numbers here are called oxidation states, which are going to be very similar to the charge of the most common ion. Okay, so if you look at column number 1, okay, lithium has a 1 and a -1, okay, and it's hard to notice here, but if you look closely, in bold, it has the 1, okay, so the bold is the common charge, most common charge, all right, so we're going to say everything in this column has a +1 charge, 1 plus charge, and its oxidation state, and turns out the oxidation state and the charge are kind of different. They kind of represent two different things, which we'll talk about in a few minutes. So the oxidation state for lithium is +1, and its most common charge is 1 plus. Okay, but you'll see that if you know this guy right here, you usually can know this here. All right. Okay, so now we're going to focus on the transition elements. Okay, like copper has 1, 4, 3, 2, 1, 0. And you notice they're all plus. I'm not sure, there might be one that says plus minus. You notice is that they leave off the pluses here. Technically, there should be a plus. So this should be +4, +3, +2, +1. If you look close at copper, you'll see that the copper here has a 2 and 1 are bold. That means those are the most common oxidation states and also the most common charges for that element. All right, so if you scan the periodic table, you see that it seems to fit. Like if you look at these guys over here, okay, the most common oxidation number is -1, and therefore the most common ionic compound is 1-. All right, so look at the bold, and the bold will be the most common ion or ions that's related to the most common oxidation state. All right, and I just went over this. All right. Okay, just notice that I went over this. Okay, I just talked about this in the previous slide. Okay, let's go over a few common elements with multiple charges. Oxidation states. Okay, it should be common, maybe common multiple charges. There's common oxidation state. First, because oxidation numbers and charges are not technically the same, you'll notice they are written differently. I told you that. Okay, so if you see this is because they say two different things. Oxygen has an oxidation state of, should be -2. This means it gains in oxidation. I mean loses in oxidation. Sorry. All right. So it has -2 oxidation state. This means it loses in oxidation, while the charge 2- means that it gains in 2 electrons. So there's going to be something that's going, when you lose in oxidation, that means you're gaining electrons. And we'll talk about that more when we get to chemical reactions. Okay. All right, so let's look at copper. Copper has 4 oxidation states, 4, 3, 2, and 1. The 4 really is +4. Okay, so it seems the copper could have 4 different charges. 4 plus, 3 plus, 2 plus, and 1 plus. And then if you notice, these 2 are in bold. So these are going to be the 2 most common ions for copper. If you look at iron has 9 oxidation states, while the 2 and the 3, I put the pluses on the wrong side, okay, +3 and +2 are bold, and thus the most common oxidation state and oxidation and ionic. So the oxidations would be +3, the ion would be 3 plus or 2 plus. Some transition elements only have 1 oxidation, like zinc and silver. This is 2 plus and plus. Okay, using oxidations, determine ionic formulas and names. So let's say I have some copper sulfate and I want to figure out the chemical formula. Okay, so if I say I have copper sulfate, and we originally would have said, because I told you copper is Cu2 plus, you would just come up with CuSO4, all right? But now what we have, that's what he said right here. But now what you have a possibility, you have 2 possible choices for copper. It could be, okay. So that's how we get this here, all right? So now you have 2 possibilities. You have copper 2 plus or copper 1 plus. So why isn't it copper Cu2SO4? Okay, how did I get that? Goes, so if it's copper with a 1 plus charge, okay, so you would need to crisscross, so you have Cu2SO4. So how do you know which one it is? Is it Cu2SO4 or CuSO4? Well, it could be either one. Then how do you know which one it is? Okay, to do this we have to identify the oxidation state of the copper in the name. All right, so if it's going to be copper 2 with the 2 plus charge, we'll put that in the name. So if it was a 2 plus charge, then it would be copper 2 sulfate. And if it was the copper with just the 1, it would be copper 1 sulfate. Okay. So the Roman numerals tells you the oxidation charge or the charge on the element. When an element just has one oxidation state or charge, you don't have to use the Roman numeral. So sodium chloride is always going to be 1 plus. So it's simply sodium chloride. You don't have to say sodium 1 chloride. Also, only the metals are given these numbers. So you wouldn't put like chloride 1 or chloride 2 or whatever. The representative elements are ones that you know the charges. All right. So so the first column and the second column, you won't be calling those sodium 1, lithium 1, beryllium 1, etc. 2, and so forth. They will just be sodium chloride and so forth. Again, the Roman numerals represent the oxidation state, and we call it, when we do this name. Okay, so there's so we can do this two ways. You can do from the formula to name, using stock system, or the other way around. So we're going to look first, getting the formula from the name. Okay, so name to formula, and you can see that's going to be pretty easy, and then we'll do the other in the next couple slides. So let's say I have manganese 5 oxide, right? And I'm just going to give you this. Don't worry about where I got that 5. But so this tells me I have manganese 5 plus, all right? We already know that oxygen is 2 minus. Okay, it's in that column. So you have initially M and 5 plus 2 minus. The charges are not the same, so you crisscross, and so you get Mn2O5. One thing I want to make sure you understand is you can write equations with charges, or the formulas with charges without. At this point, I don't care if you do it with or without, but I would prefer that you show the charges. Okay. All right. So what we're going to do now is the opposite. We're going to go from formula to name. All right. And this is going to be a little bit harder. Okay, so here's the formula, Fe0 or Fe1, FeO, Fe1 or O1. So, we usually leave off the 1. First, look at the iron to see if it has multiple oxidation states, and it does. And they're going to be, it's probably going to be either 2 plus or 3 plus. Okay, because they're the ones in bold. Next we add, know the charge of O2. O is O2 minus. And then what we're going to do is since we don't know which one of these two it is, 2 plus or 3 plus, we're going to put X in there. So we have X plus 1, O2 minus 1. And so the product of these two has to equal the product of these two, but with opposite charges. Okay, so it's simple because they balance out. The charges balance out. So so X plus times 1, it has to equal 2 minus times 1, and so X equals 2 minus, but we got to switch the charge to 2 plus. Okay, so that means that iron is 2 plus. All right, and you can see that this is what the formula is, and it's the same as this up here. And this would be iron 2, because that's a 2 plus oxide. Okay, again, we're going to try finding a formula from the name. So name to formula. All right, so V has multiple oxidation states. We can notice that by looking at the product table. So we don't know what oxidation state it is. So what you do is you can put X here, and we know sulfate is 2 minus. All right. So what you're going to get is 2 times X plus has to equal 3 times 2 minus. And so X, when you do the math, X equals 3 minus. You got to switch charts to 3 plus. And so you would get, so it'd be 3 plus that goes here. And it works out, okay? So this is going to be vanadium 3 sulfate. Okay, so first thing you have to know is is that the product of these charges here has to equal the product of these here. Okay, so why different oxidation states? In the process of chemical reactions, at least one of the elements will have a tendency to become more oxidized, get a bigger oxidation numbers, while the other atom will do the opposite, get a lower oxidation number. There are tendency for atoms to try to reach their maximum oxidation, but sometimes they can't. For instance, copper would prefer to be, in the long run, Cu2 plus, but sometimes it stalls and only goes to Cu plus. Okay. So it would like to get its biggest oxidation number of the bold type, but sometimes it stalls at the lower one. All right. When I had chemistry a long time ago, not quite 100 years ago, but almost 50 years ago, almost, we didn't use Roman numerals. We used different names to give the oxidation states. And I remember that just confused the heck out of me. The most oxidative state, like the Cu2 plus, would end in ic. And the less oxidative state would be end in us. So instead of using copper 2, we would use ic, and copper 1, we would use us. So with copper CuSO4, which is the most oxidative state, we would call that cupric sulfate. And the less oxidative state, Cu plus, would be called cuprous sulfate. Now you don't have to know this, but you're going to see in the next PowerPoint that we can relate this to what we're going to talk about with acids and bases. All right, so that's it. And there'll be homework, additional homework to work on this, and I'll send that out to you.